So counting all maps was easy. Let's make a little twist into this. Let's count injective maps. Here is the answer, and then we're going to prove it. Let m and n be two non-negative integers. Let A be an m element set, and let B be an n element set. Then the number of all injective maps from A to B is, here is one way of putting it, it's the product that begins with n and keeps going down until n minus m plus 1. And another way to put it is m factorial times n choose m, because n choose m is defined to be this over m factorial. Okay, how do we prove this? We label the m elements of A by A1 and so on AM. We can choose, so we can construct an injective map F from A to B as follows. First, we choose the value f of A1. That has to be a value in B, and B has n elements, so we have n choices for this. Next, we choose the value f of A2. This also has to be in B, but furthermore, since the map has to be injective, f of A2 should not be f of A1. So we need to avoid choosing the already chosen value f of A1. Thus, we have n minus 1 choices. Next, we choose the value f of A3. This time we have to avoid f of A1 and f of A2. There is already two values we have chosen, and they no longer work. So choosing f of A3, we have n minus 2 choices. Why n minus 2? Because these two values we have already chosen, these excluded values, they're distinct. This was guaranteed by their choices. So next, you can guess what comes next. F of A4. This time we have to avoid 3 chosen values, and they're distinct. So there is n minus 3 choices, and so on, until choosing the last value, f of AM, and there are n minus m plus 1 choices for it. Note that these choices were not independent. F of A2, we cannot reuse f of A1, so the options we have for f of A2 depend on the already chosen f of A1. Nevertheless, the number of possible options is always the same. Turns out this is enough. So in total, we have n times n minus 1 times n minus 2 times n minus m plus 1 choices, because we've just multiplied those numbers through. So the number of all injective maps from A to B is this here, and this, as we know, is this here. Note that if m is bigger than n, then this product contains n minus n as a factor. So basically, we start with a positive number here, or non-negative at least, and then we go down to a non-positive, so 0 or less. This means because we're going down by steps of 1, we must have crossed 0 at some point, and so the product has a 0 in it. Thus, this product is just 0 in this case. So we conclude that there are no injective maps from A to B if m bigger than n. And this is just the pigeonhole principle for injections. Well, one of its forms. So we have reconstructed the pigeonhole principle again, which is nice. This is not its easiest proof, but it works. So our above proof used the following fact. And now let me recall this product rule. So the product rule, I have stated it in terms of sets, but really there is a way to put it in terms of options. So consider a situation in which you have to make n choices in this order. Assume that the first, so you have A1 options in choice 1. So for the product rule, we assume that the choices are independent. You have A2 options in choice 2, and so on, and you have AN options in choice N. Then the total number of ways to make these choices is A1, A2, and so on, AN. This is just the product rule restated. Now, however, our choices here are not independent, so we need to tweak it. Here is a dependent product rule. Consider a situation in which you have to make n choices in order. Assume that you have A1 choices and options in choice 1, that's still as it was. Then you have A2 choices in options in choice 2. No matter what you chose in choice 1. So the options themselves might depend on the choice, but their number is always A2. And similarly, at the end, no matter what you chose in the previous choices. Then again, the total number of ways to make these choices is this product. If you have seen tree diagrams in high school, this is one of the things that follow easily from tree diagrams. So this can be made rigorous. I'm not going to do this. You don't need to do this in contests. It's enough if you understand this rule and how to use it. So see just 2 references. I'm going to put this in the notes. These are 2 texts which give proofs and rigorous formulations of this rule. Particularly Newstead is nice about it. So see also another reference for, sorry, 222, for a different way of formalizing the above proof, avoiding, so without explicitly mentioning the dependent product rule. The trick is instead of speaking of choices here and a sequence of n choices, you just do induction on M. But it boils down to the same argument.